Alright, so now that we know what a definite integral is, we're going to build off of this concept and introduce the idea called an accumulation function. Alright, so I got a function, here's f of x and the x-axis. An accumulation function, written like this, I'll explain this in a second. It's defined as the area under some other curve from some fixed value of x, which we typically write as a, up to x. And we write f of t dt in here. So x. Now, alright, so it's the area under the f of x curve from these, between these two values, right? Between here and here. So it's referring to this. And if x increases, then this gets pushed this way and we gain a little more area. Or if x is coming back, right, if we make x a smaller number, that's going to count for less area. Alright, so basically that's how it works. I'll do some examples in a second, but first I want to clear up this possible confusion about the notation here. The reason that we don't use x's in here is because this if I wrote x and dx and x, there would be some confusion as to which x is which. This x here isn't the same as the x that would normally pop up inside here. Alright, this is just a reference to the function under which we're finding the area. So to avoid any confusion, we typically write t's or u's or something, anything but x for the inside, because we want these variables to match, and this is just kind of a stand-in thing, just to tell us what function we're finding the area underneath. So to sort of get an idea of how this works, let me draw up another function here. So let's suppose I got a function that looks something like this, say. Alright, so this is f of x, and we're going to make an accumulation function based off of this. So I'll say a of x equals the net signed area. We'll start from 0 to x under f of t. So I could ask a question like, where is a of x increasing and where is it decreasing? What are certain values and all that? Now, since we're starting from 0, we know that a of 0 is 0, right? A of 0 is 0, because that's just the area under this point. And if x is anywhere in here, right? If I set x equal to, say, this number or this number or this number, the a is increasing for all that time, because as x increases this way, we're gaining area. Even though f of x, this little function, the little f is a decreasing function, we're still gaining area as we go, right? So it's a gain, 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 gain. Only the gain is becoming less and less pronounced because every time we go over the function, the f of x is decreasing. But you could maybe do a little sketch of a. It would start at 0 here, and it would increase all throughout here, and then it would top out here. Because beyond this point, we know that when f of x goes underneath the x-axis, this gets counted as a negative quantity because it's constructed from a definite integral. All right, so we have gain, 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 loss, 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 gain, 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 gain again. So the a of x function could look something like, say, it could look maybe something like this, and it would top out there, where this value would be the area under the curve up until this point. And then it would go down a little bit because, right, we're losing some, and then it would go back, would stop and go back up again, because past here we're gaining area again. And that's how these accumulation functions work. All right, so it's the same concept as just a standalone definite integral. If I write it with say 2 numbers, only think of this as a floating variable. All right, something that can change, and as this changes, the function from which it's constructed changes. That's basically what an accumulation function is. I do want to do a couple concrete examples before we move on here. So suppose I have, we'll say a of x equals the definite integral from 0 to x of just 3 dt. Now, this is in reference to the accumulated area underneath the function f of x is 3. So here's 3. Alright, just a horizontal line at y is 3. And we're integrating from 0 to some unspecified point x. Alright, so what that's going to give you is it's going to give you the area under the 3 curve from 0 to x. In this specific case, we can figure out what this a of x is. Alright, this a of x, this accumulation function would equal 3 times x, because it's just going to be a rectangle, right? The accumulated area from 0 to x, it has a width of x and a height of 3, so that's just going to be 3x. This happens to be one that we can actually figure out because the geometry is so simple. Another easy one, or easier one than most, is if I say a of x equals, what do we have here? Integral from 1 to x of, say, t minus 1 dt. So to give you an idea of what that looks like, the t minus 1 function, which would be f of x is x minus 1, that would be this. Just a straight line, 45-degree angle here. If we're integrating from, here's the x-intercept. If we're integrating from 1 to x, x is some unspecified point out here, the values of this function are going to give the area from under here. And in that case, since it's going to be a simple triangle, let me just squeeze down here, we could figure out analytically that this function would equal, it would be 1/2 base times height, and the base would be x minus 1. Right? It would be x, this whole distance, less 1 times the height. And the height you would get from plugging the value of x into the function itself, which would give you x minus 1 again, so it would be this. So this particular area accumulation function would be, we would symbolize it by this, but it would basically equal this. All right? If we go from 1 to x, the area is going to be whatever you get from plugging that in here. Now this is really only so useful because if you make one of these things from a function that whose area is tough to find, it pretty much reduces just to a symbol that stands for something that you could want. So for I could say this, for example, of say t squared dt. This represents, or this is supposed to represent, the accumulated area underneath the x squared function from 0 to x. Now, since there's no geometry here that we can use, it's not composed of straight lines or circle segments or whatever, we're kind of out of luck here. Right? All that we can do is just sort of talk about this function that we just made up and say, and it's really just like a conceptual tool here. All right? It doesn't really mean since we don't have a method of directly computing it right now. It just becomes something that we can talk about and discuss. So I could do this for any function I want, no matter how complicated the inside function is. But really, we're only going to have any luck evaluating these if the function inside is composed of circle segments or straight lines and all that. So, but up until now, it seems like it's pretty hopeless because these things are made from curves. And we're trying, we ultimately want a way to find the areas here, but we don't really have one. So what we're going to do, just for kicks, is we're going to take functions that are like this, and we're going to find what their derivatives look like. Again, just for kicks. So let's see. Suppose we have, and this will actually show us the key to figuring out how to evaluate them exactly. So suppose we have some function, alright, doesn't matter what it is, f of x, here's f of x, and we're going to create an area accumulation function, a of x, and we're going to define it as the definite integral from a I'm not even going to specify where A is. It could be anywhere. From A to X under the curve f of t dt. So what would the derivative of A of X look like? That's what we're here to figure out. So again, just for kicks, we're really just kind of screwing around here. We're going to take something like this and differentiate it and just see what pops up. So what do we got to do? We need the definition of the derivative as a limit, so I'm going to write that. That will be to find A prime, right, A prime of X is going to equal, let me get some space here, the limit as h approaches 0 of A of X plus H minus A of X all over H. Alright, step 1. So let's see, let's start to break this down. That equals the limit as h approaches 0. Now A of X plus H is the definite integral from little a to X plus H of f of t dt. I'm just filling in what this is based on what we said it was back in the beginning here. So that's going to equal that minus accumulation from A to X of f of t dt, and all this is over H. All right, limit as h approaches 0. So what we're going to do with this is we're going to play around here using the properties that were talked about in the last video, and I'm going to switch the boundaries here, thus changing the sign of the definite integral. So that'll be equal, I'm going to write out all the steps I can so this is as clear as possible. Limit as h approaches 0, definite integral from A to X plus H of f of t dt. When I switch the boundaries, I change the sign, and that'll be plus from X to A of f of t dt, again all over H. Can you see that? Yeah, again all over H. And then using another property of the definite integrals talked about in the last video, I'm going to combine these into one expression, because the definite integral from X to A plus the definite integral from A to something else equals the definite integral from X to that something else. So I'm going to come over here and just rewrite it again, keeping the limit as h approaches 0, and I'm going to write 1 over H. Instead of writing everything as like a big fraction, I'm just going to write 1 over H multiplied by the definite integral from X to X plus H of f of t dt. And so at this point, what I'm going to do is I'm going to come up with a different way of writing this definite integral here. And for that, I'm going to need a little bit of side work. So I'm going to bring this out. Suppose that we have some function here. All right. What does this mean? This means the area under the f of t function, whatever that is, from X to X plus H. So regardless of what the function looks like, all right, what it's talking about for the little function here is the area of this segment here, and we're going to take the limit as h approaches 0. So it's like as this line here closes in on this original line. Now it's referring to the exact area of this sort of curvy, like shaped region here. But what I'm going to do is I'm going to exchange that definite integral expression. I'm going to switch this out, right? X plus H of f of t dt. I'm going to rewrite this as using what I call the rectangle principle. The rectangle principle is that any area that you write, any area under a curve, can exactly fit into a rectangle of certain size. It'll be something like this. All right, check it out. The area under the curved region looks like it would almost as I have it drawn anyway, almost exactly fit inside this rectangle. And that's always going to be possible. All right. For some, you'll be able to say, if we took this area here and just kind of rearranged it and smushed it around, we could exactly fit it into this spot out here. So we're going to replace the area of this curved region with the area of a rectangle. And that's always going to be possible no matter what this function looks like. And the way I'm going to choose to say this is that we're going to replace the integral of x to x plus h of f of t dt with this rectangle whose width is h and whose height is f of some number that's between these two. So I'll call this special number, say, x bar. Now, there's going to be an x bar no matter how big or no matter what this original region looks like, right? If I make it big or small, for example, if I take h and I make it larger, that's going to push this side out this way more. The only thing that's going to change is where x bar is. But for any kind of arrangement like this, I'll always be able to find some x bar no matter what the region looks like. So we're guaranteed to find such a number. So h times f of x bar, I'm going to say. So what used to be this, I'm going to cash that out and replace it with this. Because I can. That's always going to be possible no matter how small of a region I'm talking about here. No matter how small h is, right? If h, let's say h was right here, then the area would be this little sliver here. And x bar would still be something in between there. It would be something around there. Right? So there's always going to be an x bar no matter what interval I'm talking about. So I'm going to replace this with this in the original. And that'll give me, so that's going to leave me with the limit as h approaches 0 of 1 over h multiplied by what used to be this will now be h times f of x bar. Some special value guaranteed to exist somewhere inside the interval between x and x plus h. Well, if you look at it that way, the h's cancel, and that gives you the limit as h approaches 0 of f of x bar. Now, what do you suppose happens as h approaches 0? Well, let me come back to this again for a second. If I draw up another one, no matter what the function looks like, let's say it's this. If here's x, let's say h is real big. Say it's way out here, x plus h. Okay. As we take h, as h approaches 0, this side is moving this way. So it's closing in, and there's always an x bar somewhere in between x and x plus h. So as h approaches 0, x bar, which is always sandwiched inside here, approaches, so as h approaches 0, x bar approaches the value of x that we had originally started with. It approaches this number because it's always sandwiched in between. And so this is actually the limit as h approaches 0 of f of x bar is actually f of x. And what does this all mean? Well, this actually has a very profound meaning. What have we discovered at this point? We have discovered that if we invent something like an area accumulation function like so, that gives the net signed area from x equals from some arbitrary value to x, and we call this a function, and it is a function, it's something that we can talk about, it has inputs and outputs, each input goes to exactly one output, so it's definitely a function. And you can see that the area gaining function, right, it's definitely also a function that is differentiable, right? As x, say, slides out here, it's reasonable to assume that the area is increases nicely as x increases. So it's a pretty nice, smooth looking function. So it does definitely have a derivative. But what we have figured out was, if we take such a function, which was up until now just something that we just thought of, and we differentiate it, what we get is the function that was being accumulated. Okay? The whole purpose of this, the importance of this, was to show that. I'll write it down succinctly here. If a of x is an accumulation function between a and x for some for some function f of t littler f of t dt, then its derivative, a prime of x, is just the function that's being accumulated. This is the money shot. Alright, this is of prime importance because it tells us, check this out, look at what we can do with this. We might not know what a of x is, but we know what its derivative is. What this tells us is that the derivative of the function we want to find information about is known, is something that can be calculated. Okay, so it's kind of like saying this: if I gave you some mystery function, say question mark of x, and I say I don't know what this function is, but I know that question mark prime is, say, x squared plus 1, then you can take this information and reconstruct what question mark must be by taking an antiderivative, right? To go from question to question mark prime, we use differentiation. So to reconstruct question mark, we just anti-differentiate this to give us what the original thing is. If the derivative of question mark is this, then question mark must be 1/3 x cubed plus x plus a constant. And that's how we figure out what these area accumulation functions are, by antiderivatives. That's why we study antiderivatives. So to recap, we can figure out what these area accumulation functions are because we know what their derivatives are. And let me just do a couple of examples of this before I wrap this up in the statement of the actual theorem. So I want to show you this concept in action. Suppose that we have some function, let's say a of x. An accumulation function is going to be an accumulator from 1 to x of, say, t squared dt. Now, that is a reference to, under the area, it's going to be the area under the x squared curve, right? From 1 to wherever I say x is out here. Alright. Now, what is that function explicitly? Well, we don't know what it is, but we know what its derivative is. We know that a prime of x equals x squared. Therefore, to figure out what a is, all we have to do is anti-differentiate, and we get a of x, which is this, must be 1/3 x cubed plus a constant, an antiderivative of this. So that's it. That's really all it takes. Now you might ask, well, what's that plus a constant doing there? How does that help us figure out what the areas are? Well, by the way we defined it, we want a of 1, in this case 1, to be 0. So when we know that a of x is 1/3 x cubed plus c, and we also know that a of 1 must be 0, we plug 1 in and we get 1/3 times 1 cubed is 1 plus c must be 0. Therefore, c is going to equal minus 1/3. And the actual function itself, a of x, when written not this way, but written, I guess written out nicely, is actually 1/3 x cubed minus 1/3. If we start from 1. Anyway, see, the constant of integration is going to be something different depending on where we start from. If we did the if we had defined a of x to be the definite integral from 2 to x, everything would have been the same. Its derivative would have still been x squared. So so a of x had to be 1/3 x cubed plus c. But in this case, a of 2 would have had to have been 0. and instead of getting 1/3 or minus 1/3 for the constant, what we would have wound up with would have been minus 8/3. But this is how all of these go, and it doesn't matter how complicated this thing is as long as we know how to find an antiderivative. So let me do one more example of this. We'll define another area accumulation function as the definite integral from 0 to x, say, of sine t dt. I want to know, what is this function exactly? Well, I don't know, but I know that its derivative, let me try to squeeze it up here. I know that a prime of x must be sine x. Therefore, I know that a of x must be an antiderivative of sine x, namely minus cosine x plus c. And so to figure out what the constant of integration is, I know that I have defined it so that a of 0 should give me 0. So, let me write it over here. So, a of 0 equals the minus cosine of 0 plus c, which has to be 0. The cosine of 0 is 1, so that's minus 1 plus c equals 0, so c is 1. Whoops. And can you see that? Yeah. And so therefore the function itself, a of x, this is actually the function minus cosine x plus 1, right? Via antiderivatives. Now I'm applying this concept to these specific functions here. Let me wrap this up by doing it with a unspecified function, little f of t. So what did we find? Right? We said that a of x, functions defined by definite integrals, we'll say from a to x of f of t dt. We know that the derivative of a, or rather, we know that a prime of x must equal f of x. Therefore, a of x, this function itself, must equal an antiderivative of little f, which I write as big F of x plus a constant. Right? So when I write a big F, I'm talking about some antiderivative of little f. So we have a of x, which equals this, from a to x, of f of t dt, actually equals some antiderivative of f plus a constant. How do we figure out what that constant is? Well, we want a of a to give us the integral from a to a, which should give us 0. So that's going to equal f of 0, I'm sorry, f of a. Right? We're replacing x with a, f of a plus c. Therefore, in this case, from this equation, the constant must be minus big F of a. And so, to cap this off, we have a of x equals antiderivative, definite integral, from a to x of f of t dt, which equals big F of x minus big F of a. And basically this right here is the fundamental theorem, because if we want from this a of b, what we're referring to is the net signed area under the f of t, under the small f curve from a to b, and that's going to give us the antiderivative evaluated at b minus the antiderivative evaluated at a. And this is typically what's referred to as the fundamental theorem of calculus, or part 1 or part 2, depending on whose book you read. Part 1 was actually what we discovered when we found out that the derivative with respect to x of a function defined by a definite integral of f of t dt. When we differentiate this, we get little f of x. That's part 1. Or part 2, again depending on whose book you read. But this is the statement of the fundamental theorem of calculus here. So it connects derivatives of accumulation functions and how to find accumulation functions exactly via anti-derivatives. And that's it. If you could, please leave me some feedback about this video because it's my first time really exploring and teaching it this way, and I want to know whether it lands or whether it doesn't, or what's good or what's bad or what, because I think that the fundamental theorem is actually something that's really, really important to understand, but just winds up being something that most students just memorize and don't really grasp. And I want to know how this video worked out for you, so please let me know, and that's it.